Okay, well, hello everyone. Well, my name is Jorge Antonio Morales Soto. I'm working with Dr. Juan Carlos Arteaga. We are from the Instituto de Física y Matemáticas de la Universidad Michoacana, from the HOC collaboration. And what I'm going to talk about is about the all-particle energy spectrum of cosmic rays from 10 TeVs up to 1 PeV, measured with HOC. The outline of the presentation is going to be a brief introduction, then a little bit about what's the HOC Observatory, then about analysis and results, and finally, the conclusions. So, well, the first results of the energy spectrum that the HOC collaboration presented were published in 2017, and the measurements went from 10 up to 500 TeVs using 8 months of data. These are the results over here with the blue squares with their corresponding error band, and they are compared with the measurements from other experiments. One of the main characteristics of these results was the presence of a new structure over here in the spectrum at around some tens of TeVs. And the motivation to update these analyses are in this work are to extend the study of the measurements of up to 1 PeV. This way we can reach the other indirect cosmic ray experiments, and also in the low energy region to also contribute in this part where the direct measurements dominate. Another of our main goals are to increase the statistics in the analysis and also to reduce the systematic uncertainties that are in the results, using better simulations that describe better the performance of the detector. Now, going to what's HOC, we already heard a little bit about it, thanks to Dr. Juan Carlos. It is located between the Pico de Orizaba and the Sierra Negra volcanoes in Mexico, in here. You can see the map here, and you can see a nice picture of the Pico de Orizaba in here. It is located at 4,100 meters above sea level. It has an area of 22,000 square meters, of which we have 62% of physical coverage. And in total, we have 300 water Cherenkov detectors. There is a scheme of the detectors in here. We have 4 PNTs in each one of them, giving us a total of 1,200 photomultipliers. And well, one of the main goals of the collaborations are to extend the astrophysical measurements of gamma rays up to 100 GeVs, and also to study cosmic rays between 100 GeVs and 1 PeV. Now, for the simulations, in HOC, we use Corsica, of course. And within Corsica, we use two hadronic interaction models, which are FLUCA and QGIS-JET 204. FLUCA, we use it for energies below 80 GeVs, and QGIS-JET 204, we use it for higher energies, higher than or equal than 80 GeVs. To simulate the interaction of the secondary particles and the detector, we use the package JAN4, and we have 8 species of nuclei from hydrogen to iron, and these are weighted according to fits to data from AMS, CRIM 1, 2, and Pamela. And these are generated with energies between 5 GeVs and 3 PeVs, and the shower cores are distributed within a circular area of a radius of 100 meters that is centered at HOC, with zenith angles less than 70 degrees. Now, we use some quality cuts over the simulations and our measured data this way, so we can diminish the systematic effects over the reconstruction, the energy resolution, the core position, and the arrival direction. This is reflected directly when we estimate the bias in the resolution of these quantities. And here we have an example of the energy resolution. And well, in other words, what we're going to do is to select events that are successfully reconstructed that have a zenith angle below 35 degrees. This is what Dr. Juan Carlos mentioned earlier. We do this to diminish the saturation at higher energies. This way we can go up to 1 PeV. Also, we selected events that activated at least 60 channels in a radius of 40 meters from the shower core. We're also using shower cores that were reconstructed mainly inside HOC's area and that activated more than 3% of the available channels. And well, at an energy of 10 to the power of 5.9 GeVs, we have that the energy resolution is around 26%. You can see it here. And similarly, we find that the core resolution is of 19.5 meters, and the arrival direction resolution is of 0.7 degrees. Now, moving to the analysis, the first step is to select a data sample. So the data sample that we selected for this work was taken between January 1st of 2018 and December 31st of 2019. Oh, sorry, there's a typo. Should be 2020. And we only selected showers that are between this energy region of 10 to the power of 3.5 up to 10 to the power of 6.2. We have a total effective time of 1,062 days. It's roughly 3 years. And this is our differential solid angle, sorry. And in the left side, we have the measured energy distribution after the quality cuts. This hasn't been corrected yet for migration effects. So the next step in our analysis is to correct these effects using unfolded method. We're using the Bayesian unfolding, which I assume most of you or all of you are familiar with. So we're not going into details, but basically what we need is a response matrix, which is an input from the Monte Carlo data. We plug it into the Bayes formula, then we get the true event distribution, and finally the final distribution. And for the iteration depth, we are basing a criteria of finding the minimum of the weighted mean square error. And the other two ingredients for the reconstruction of the energy spectrum are inputs from Monte Carlo data in here. We have the response matrix, which I just mentioned that we use in the Bayes unfolding. In here we have the reconstructed energy, and here we have the primary energy, and in the theta axis we have the probability. So from this plot, you can see for energies higher than 10 to the power of 4, Hawk's response becomes linear. And the other input that we use from the Monte Carlo data is the effective area. This is how we estimate it. From here, you can see that the maximum trigger and the reconstruction efficiency at Hawk is achieved for energies higher than 10 to the power of 4.5 GeVs, as you can see from here. So now that we have all the ingredients, we can go and have our final result of the energy spectrum using this equation over here. We have the unfolded energy distribution, the differential energy, the differential effective time, the differential solid angle, and the effective area. In here, we have our results from this work. That is these black dots with its corresponding error band. And also we have uncertainty in the primary energy that goes from plus minus 9%. And it is also comparing here with the results of the energy spectrum that Dr. Juan Carlos just showed us. And the contributions to the systematic on the error on the flux. We have these contributions over here. We have the PMT charge, efficiency, late light, the threshold, the composition model, the effective area, the seeding unfolding, the smoothing in the unfolding, and the unfolding technique, and the differences between runs. So at an energy of 10 to the power of 5 GeVs, we have that the higher contributions to these systematic uncertainties are given by the PMT efficiency and also by the composition model. And at this energy of 10 to the power of 5 GeVs, we have that the total uncertainty varies from minus 3.7% up to 9.8%, as shown in here. And these are the asymmetrical error bands corresponding to the systematic uncertainty, this solid black line, and the statistical uncertainty. So at an energy of 10 to the power of 5 GeVs, our statistical relative error is around plus minus 0.01%, and the systematic relative error is from minus 3.7% up to 9.8%. And if we compare the values from the measurements of 2017, well, you can see that we reduce significantly this systematic error in our analysis. And this is how this result is compared with the measurements from other experiments. In blue dots, we have this result with its error band. And we compared with experiments like Argo, iStop, Cascade, Taiga, Tibet, and Tunka. As we can see from here, at high energies, we are in agreement within systematics with the results from Nucleon and also with the results from Taiga high score in here at high energies. And also, finally, we also found the structure in the energy spectrum, tens of TeVs. To study the significance or the presence of the break in the spectrum, we made fits to the results. You can see them in here in this plot in the right side. So we made two fits using a power law and a broken power law. And these are the results of the parameters using the fits. We obtain a spectral index using power law of minus 2.65 with its corresponding error. And this is the value of the chi-square and the number of degrees of freedom that were used in the fit. And similarly for the broken power law, these are the results for the spectral indexes. We have the first one, which is minus 2.5, and the second one of 2.7. The position of the rake was found at 31 TeVs, and this is value of the chi-square using 5 number degrees of freedom. And to test this, we defined test statistics using this way by the chi-square, and we obtained a value of 418.77. And once we have this result, what we did next is to generate Monte Carlo toy spectra, this way to validate which one of the two scenarios best describes our result. And we found that the scenario of the broken power law is favored by a significance of 3.9 sigmas. And finally, the conclusions. We extended the measurements of the total energy spectrum of the cosmic rays with Hawk up to 1 PeV. When comparing these results with the ones published in 2017, we managed to reduce the uncertainties on the flux in this work. We also confirmed the presence of a knee-like structure in the energy spectrum of cosmic rays. In this study, this break is located at around 31 TeVs. And also, in addition to the results from Nucleon, Hawk's results on the all-particle energy spectrum offer a bridge between indirect measurements and direct measurements.